Hi, this is an example problem from Chapter 31 on the exponential decay of radium-226. So we're given some data about radium-226. It undergoes alpha decay. It has a half-life of 1600 years, and we have a sample that initially contains 3 × 10⁻16 nuclei of this radium-226. We're asked to determine part A, the initial activity in SI units and units of curium. So the idea of activity, that is a measure of the number of decays of these atoms, which are always accompanied with the release of a radioactive particle. So how many alpha particles are being emitted per unit time? That's what activity is. When we talk about exponential decay, it follows a exponential decrease law here. So each half-life, T1/2 we call it, if you start with a certain amount of nuclei after one half-life, the amount remaining has been divided by 2. And after a second half-life, that amount is divided by 2, etc. That follows exponential decay. Now, it could be a lot of things. It could be the number of nuclei that is decreased by half. It could also be the activity, the amount of activity, because remember, activity is the decays per unit time, and that's how many nuclei you have decaying. So either of those, whether it's the number of nuclei, whether it's the activity, they both decay exponentially. At any given time t, we can calculate a value of the number of nuclei or what the activity is at that moment. Now, another equation for activity here, at any moment in time, if you know what the value of n is here, the activity is given by lambda times the number of nuclei, and lambda is what we call the decay constant. It is related to the half-life here. The half-life T1/2 is equal to natural log 2 divided by the decay constant. So we can use that equation here. And we saw that the activity at any given time is equal to the decay constant lambda times the number of radioactive nuclei at that time. If we want, we can go ahead and just solve for lambda in terms of T1/2, since we know what that is, and we'll see that that's going to be equal to ln of 2 divided by T1/2, and so we can write the activity in this case as ln 2 over T1/2 multiplied by n, and we'll just put in the numbers there. So we've got ln 2 divided by 1600 years multiplied by n. This is the initial activity. We've got 3 times 10 to the 16th nuclei. And now, right now, I've got units of years. I want to convert this to seconds. And so the conversion I looked up on Google tells us that for 1 year, we've got 3.154 times 10 to the 7 seconds. Cancel our years out, and we're going to get an answer here. And this comes out to 4.12 times 10 times 10 to the 5th. And that's 1 per second. What that means is decays per second. And so another unit to write 1 over seconds for activity is becquerel, BQ. And that's the SI unit of activity here. Number of decays per second, becquerel. Now, this is the initial activity, and so typically we call this A0, since it's the beginning amount at time t equals 0. Now, it also asks us to convert this to Curie, which is another unit that we often use for activity. So to convert to Curie, we just need to look up the conversion factor of becquerel to Curie. And that's given here. 1 Curie is equal to 3.7 times 10 to the 10th becquerel. And so we convert this to Curie, and we get a value equal to 1.11 times 10 to the minus 5th Curie. All right, let's look at part B here. The number of radium nuclei remaining after 4,800 years have elapsed. So now we're going to look, we started out at t equals 0 years. And at that time, we had 3 times 10 to the 16th nuclei. Now, 4,800 years later, how many are remaining? Well, we need to use an equation for exponential decay to figure that out. And here we can use both of these apply. This is the number of remaining radioactive particles. This is the activity. We're looking at this one here. So we can go ahead and copy that equation and use it. So we know the initial number here. We're going to try to find this at this value when t is equal to 4,800 years. And we can calculate the decay constant if we want. However, we're given the half-life, and we know that they're related in this way. So it's better to just plug that in. So n0 is equal to e raised to the power negative. Now for lambda, I'm going to plug in the ln2 divided by t1/2, and that's all still multiplied by t. So the good thing about using the t1/2 is now, since we're given years as units in both of the times, we can just stick with that value. So to go ahead and put in our data, let's go ahead and do it. So n of t is equal to 4,800 years. We start with n0, 3 times 10 to the 16th nuclei remaining initially. That's going to be e to the negative. And here we have ln2 multiplied by the time, 4,800 year, divided by the half-life, 1,600 year. And the years cancel. We've got a dimensionless quantity here, which we need for the exponential function. Put that into the calculator. We get a value equal to 3.75 times 10 to the 15. Now you may have noticed that 1,600, 4,800, well, that's a multiple of 3 half-lives. So in a sense, we could say that we've divided the number by 2 3 times to get this value also. But the equation always works, and a lot of times you don't get the exact number of integer half-lives, and so you got to just use the equation anyhow. Finally, to calculate the activity at this later time, we can go back and just use the same equations we did before. So for part C, now we're going to look at the activity at a later time, 4,800 years. That's going to be equal to the same equation as we used before, and now n in this case is evaluated at 4,800 years. We can basically use the same equations we did before here. We just need to update the number. Instead of 3 times 10 to the 16th, we've got 3.75 times 10 to the 15th. And putting that into the calculator, we're going to get a value for the activity at this later time, which is equal to 5.15 times 10 to the 4th decays per second, or becquerel, since we are in SI units here.